Okay, so now let's return to the likelihood function that we already set up. So we were thinking about a case where I have n observations numbered x1 to xn that all come from an exponential distribution with parameter lambda. And so this exponential distribution has the following PDF. And it's worth noting here that, well, what's the significance of this lambda? If we take the expected value of this exponential distribution, well, the expected value of x is equal to 1 over lambda. So lambda tells us is actually the reciprocal of the mean of the expected value. Okay, so we want to find the maximum likelihood estimate. So what we need to do is figure out where the derivative of L is equal to 0. And in order to take the derivative of this product with respect to lambda, so now our variable is lambda, it's going to be kind of messy like this. So here's a nice little trick that we can do is I'm going to introduce a new function. I'm going to call it y, which is going to be the natural log of this likelihood function. And the reason why is natural logs of products can be written as sums. And it's a lot easier to take the derivative of sums than it is to take the derivative of a product. But we'll come back to that in a second. So the thing that we want to observe here is that the value of theta that maximizes the likelihood function that's also going to maximize the value of y, which is the natural log of this function. Okay, so the natural log is an increasing function. So the larger the thing that I plug into the natural log, the larger the result is going to be. So instead of taking the derivative of L, what I'm going to do is I'm going to find out what value of theta makes the natural log of L greatest. And that value of theta, therefore, would also be the value that makes L the greatest, since the larger the thing that I plug into the natural log is, the larger the natural log. Okay, so why is it nicer to take the derivative of the natural log of this? Well, in this case, this function, if we take the natural log of that, we would get the natural log of lambda to the n plus the natural log of e to the minus lambda times the sum of our xi's. And so for this, the natural log of lambda to the n, we can just bring the n down. So now we've got natural log of lambda. And for the second term, if I take the natural log of e raised to any power, they're going to undo each other. And so I'm going to get n times the natural log of lambda plus negative, and then the power here was lambda times the sum of the xi's. So when we do this operation, the natural log and the e, they are inverses of each other, and all that we get is minus the sum of the xi's. And I'm being a little bit lazy here, but we have n observations, so I is going from 1 to n. And so now the whole goal here is we wanted to maximize the function L. And that would have required us to take the derivative of this product. So we would have had to do some product and chain rules, and it would have gotten a little bit messy, whereas if I now take the natural log of L first, I get this sum. And now what I want to do is figure out, well, when is the natural log going to be greatest? So what value of lambda is going to maximize that? So now we're going to take the derivative of the log of the likelihood function with respect to lambda. So taking the derivative of the first one over here, the derivative of natural log of lambda is 1 over lambda. So I get n times 1 over lambda. And for the second piece, if I were to take the derivative of this with respect to lambda, this stuff is all constant, right? Because we would have a set sample. So we would just add up all of the observed samples. That's some constant. And so if I take the derivative of this with respect to lambda, this derivative would give me minus 1 times this constant. So on the second term, we're going to get minus the sum of the xi's as I goes from 1 to n. So here's our derivative of the log of the likelihood function. And now I'd want to know what value of lambda is going to make that equal to 0. So now if we wanted to solve this for lambda, we would get that lambda is equal to n divided by the sum of the xi's. So that would be our maximum likelihood estimate for the value of lambda. And so what we've observed is that this value of lambda makes the natural log of L greatest. So if it makes the natural log of L greatest, that must mean that it also makes the value of L biggest. So there's our maximum likelihood estimate. And again, hopefully this makes some sense, because what this actually gives us is the reciprocal of the sample mean. So this also matches up, our maximum likelihood estimate matches what we might have expected to get as the value for lambda. So to summarize this, one kind of trick to keep in mind here is that oftentimes these likelihood functions, because they're products of f of x1 times f of x2 times f of x3, that it's oftentimes easier, instead of taking the derivative of L, to actually first take the natural log of L and look at what's called the log likelihood function, and then find the maximum of the log likelihood function. Okay, so there's a lot going on here. So just take a breath, and we're going to move over to the next slide, where we're going to take an example from start to finish.